Theovis, the idea made visual.
Heat spreading through metal, a drum's vibration, the electric field around a charge. These look like completely different physics.
And yet, you're gonna tell me they're secretly the same equation, aren't you?
I am. One operator sits at the heart of all of them, and it's built from a single, almost childishly simple question.
Okay, what's the question?
Pick any point in a temperature field. Ask only this: is this point hotter or colder than the immediate neighborhood around it?
That's it? Just compare a point to its surroundings?
That's it. Ask it everywhere at once, and you've built the Laplacian. Hold on to that question. We'll keep coming back to it. Here's a grid of temperatures. For each cell, average its 4 neighbors. Then subtract the cell's own value. That difference is the discrete Laplacian.
So, a cell hotter than the average around it gives a negative number?
A peak poking above its surroundings is negative. A dip below them is positive. The Laplacian measures how much a point bucks its local average.
Let's put a number on it. Take the parabola x squared near x equals 2. Sample it one step on each side and combine. Right minus twice the center plus left.
9 minus 8 plus 1 is 2, and the true second derivative of x squared is also 2.
So neighbors minus center isn't an analogy for curvature. In the limit, it is the second derivative. In smooth space, it's the sum of second derivatives. But there's a second reading, the divergence of the gradient.
Gradient points uphill. Divergence asks whether something is spreading out from a point.
So the Laplacian also asks, at this point, is the uphill flow diverging away or converging in? Same question, wearing a vector calculus coat.
We can measure how a point compares to its neighbors, but what makes anything happen?
Make the rule dynamic. Let every point change in time at a rate equal to its Laplacian. Hot spots above their neighbors, cool. Cold dips, warm up.
Everything is constantly pulled toward the average of what surrounds it.
And that one sentence is the heat equation. Watch a jagged temperature profile evolve under that rule. The sharpest spikes collapse first, then the gentle bumps, until everything relaxes towards smooth.
It's like the roughness gets sanded away. Fastest features first.
That's diffusion. Cream in coffee, blur on an image, heat fleeing a poker. Same Laplacian, same smoothing, every time. Rate of change in time equals a constant times the Laplacian in space. That tiny equation runs an astonishing amount of the physical world.
And the constant just sets how fast the smoothing goes.
Concretely, a cell at 80 degrees, neighbors averaging 50. Neighbors minus center is minus 30.
Negative. So this point is hotter than its surroundings, and the heat equation makes it cool toward 50.
Run that everywhere, step after step, and the whole field marches toward agreement with its neighbors.
So where does the smoothing stop? when does a point stop comparing unfavorably to its neighbors?
When the Laplacian is zero everywhere, when every point already equals the average of its neighbors. Functions like that are called harmonic.
No point poking above or dipping below its surroundings.
Harmonic functions have a gorgeous property. The value at a point equals its average over any circle drawn around it. Exactly.
Which means the hottest and coldest spots can't hide in the interior. They're forced out to the boundary.
That's the maximum principle, and it falls straight out of Neighbours minus center being zero. And here's the payoff on something real. Take an actual photo and apply Neighbours minus center to every pixel's brightness.
The flat regions go dark. They match their neighbors, but the outlines light up.
Where brightness changes fastest, the Laplacian is large. That's edge detection, the exact same operator now sliding across pixels as a convolution. Change the time rule again. For a vibrating membrane, acceleration is proportional to the Laplacian. The more a point bulges above its neighbors, the harder it's pulled back.
So the same operator that smooths heat also supplies the springiness that makes things oscillate?
Exactly. And a drum can't vibrate in any old shape. Only in special ones, the Laplacian returns unchanged, just rescaled. These special shapes are the eigenfunctions of the Laplacian. Each keeps its form and simply breathes up and down.
And the amount it gets rescaled is the eigenvalue.
Which sets the pitch you hear. The shape of the boundary picks the modes. That's why you can almost hear the shape of a drum. Put numbers on the music. For a square drum, the eigenvalue is pi squared times m squared plus n squared.
So the 2-1 mode sits at 5 pi squared, about 49, against the fundamentals 20.
Pitch goes as the square root, so that mode rings about 1.5 times higher. The geometry literally tunes the instrument. Flip one sign and one time derivative, and diffusion becomes vibration. Same operator, opposite character.
Smoothing and springiness, both from Neighbours minus center.
On a line, which functions does the Laplacian return unchanged? Sines and cosines. Their second derivative is just minus themselves.
So the Fourier basis isn't arbitrary. We use sines and cosines because they're the natural modes of this operator.
That's the deep reason Fourier analysis and differential equations are joined at the hip. Same question asked on a line. Add a source, and the Laplacian stops being zero. In electrostatics, charge density tells the potential exactly how much to curve at each point.
So a charge is literally a place where the potential refuses to equal its neighbor's average?
The same Poisson equation governs gravity and steady flow. Wherever there's a source, a Laplacian is set equal to it. And it doesn't need smooth space at all. On any network, compare each node to its connected neighbors. That's the graph Laplacian, the workhorse of clustering and data science.
The same Neighbours minus center, now on friends in the social graph, or pixels in an image.
One idea, reused everywhere. People need to ask how a thing compares to what's around it.
So, back to the one question. That really was the whole video, wasn't it?
Heat, waves, drums, electric fields, networks, images. Every one is that single question, asked everywhere at once. How does each point compare to the average of its neighbors?
Answer that, and you're not learning 6 topics.
You're learning one, wearing 6 different costumes. If you want to go deeper, these are the classic sources. Evans for the PDE theory, Strang for the discrete and graph Laplacian, and Kax's famous question about hearing a drum.
Corrections and better references are always welcome in the comments.
Next time you meet del squared in an equation, don't read it as a symbol. Read it as a question. How does this point differ from its neighbors?
Subscribe to follow the series, and we'll see you in the next one.
If it finally clicked, subscribe. It really helps. And I'll see you in the next one.